Somewhere in a hospital right now, a nurse is scanning a fridge full of blood bags, looking for one specific label. Not A, not B, not AB. She's looking for O negative, the bag that can go into almost anyone without warning, without waiting, without a match. It's the blood type doctors reach for when there's no time left. And yet the thing that makes it so valuable is also the thing that, for most of human history, made it dangerous to carry. Today we're talking about Rh-negative blood, the roughly 15% of people whose red blood cells are missing a protein that almost every other human and every one of our closest animal relatives carries without exception. Where did this gap come from? Why did evolution allow it to survive when it should have wiped itself out? And why does it keep showing up in the same handful of places on the map, generation after generation? Stick around, because this one gets stranger the deeper you go. Let's start with the basics, because the basics are already strange enough. Blood type is usually explained through the ABO system, B-A-O, but there's a second layer sitting right underneath it that most people never think about, the Rh factor. It's named after the rhesus macaque, the monkey species used in the original research, because scientists first found this particular protein sitting on the surface of the monkey's red blood cells. When researchers checked human blood against it, they discovered something odd. Most people's blood cells carried a matching protein, but a noticeable slice of the population, roughly 1 in 7 people worldwide, didn't have it at all. Their blood simply didn't respond. Where a positive sample would react and clump when exposed to certain antibodies, negative blood just sat there, quiet, unreactive, invisible to the test. That absence is what defines Rh-negative blood. It isn't a different protein. It isn't a mutation that adds something new. It's a deletion, a piece of genetic code that, in 15% of us, simply isn't there. Now here's where it gets interesting, and this is the part that actually pulled scientists down the rabbit hole. When researchers went looking for this same gap in other primates, chimpanzees, gorillas, orangutans, macaques, every close relative we have on the evolutionary tree, they didn't find it. Not in isolated pockets, not in a handful of outliers. The Rh protein appears to be universal across primates studied so far. As far as researchers have been able to determine, humans are the only primate species known to carry a version of this gene that can simply switch off in a meaningful share of the population. That's not a small footnote. In evolutionary biology, traits shared across an entire family tree are usually considered stable, locked in because they serve some basic function that every branch of the tree still needs. For a trait like that to vanish in only one branch, and only in some of that branch, is unusual enough that it's kept geneticists arguing for the better part of a century. If Rh-negative blood was scattered evenly across the globe, this would be a much shorter video. It isn't. When researchers began mapping where this blood type actually clusters, the pattern pointed toward one very specific corner of Europe, the Pyrenees, the mountain range straddling the border between Spain and France. This is Basque Country, home to a population that has puzzled anthropologists for a different reason entirely, long before anyone was drawing blood samples. The Basque people speak Euskara, a language that linguists classify as an isolate, meaning it has no confirmed relatives among any other language family on Earth. It isn't related to Spanish, French, Latin, or any other Indo-European tongue spoken anywhere near it. For a language to survive for centuries while completely surrounded by unrelated languages is already remarkable. But when blood typing became widespread in the 20th century, researchers found something that lined up almost too neatly with that linguistic isolation. Basque populations show some of the highest concentrations of Rh-negative blood recorded anywhere in the world, with some regional studies putting the figure well above the global average of roughly 15%. The leading explanation isn't mystical, even if it sounds like it should be. Geography did the work. The Pyrenees are rugged, difficult to cross, and historically kept large-scale migration and mixing out of the valleys tucked inside them. While the rest of Europe experienced wave after wave of invasion, resettlement, and genetic blending over thousands of years, Basque communities stayed comparatively isolated. A population that doesn't mix much with outsiders tends to hold on to whatever genetic quirks it already has, simply because there's nothing diluting them. Some researchers have floated the idea that vast populations may represent a genetic through-line to some of the earliest human groups that settled in Europe after the last ice age. Though this remains a debated hypothesis rather than settled fact, and newer ancient DNA studies continue to complicate the simple version of that story. Still, the pattern holds beyond the Pyrenees. Move north along the Atlantic coastline, into Brittany, into the old Celtic regions of Ireland, Scotland, and Wales, and Rh-negative rates stay noticeably elevated compared to the rest of the world, often cited in the 20 to 25% range in various regional studies. It's the coastal, historically isolated edges of Western Europe, again and again, that keep showing up as hotspots. Whether that's a coincidence of geography or genuine echo of ancient population movements is still being debated. But the map itself isn't up for debate. It's there, and it's consistent. There's a phrase that's been used for centuries to describe European aristocracy: blue blood. The traditional story behind it is simple enough. Wealthy nobles rarely worked outdoors. Their skin stayed pale, and pale skin makes the bluish tint of veins more visible underneath it. That's a perfectly reasonable, boring explanation, and it's probably the correct one for the phrase itself. But dig into European royal genealogies and you find something less poetic. For centuries, ruling families intermarried deliberately, cousin to cousin, generation after generation, in an effort to preserve bloodlines and consolidate power. That kind of closed breeding pool has consequences, and one of the most famous is hemophilia, a blood-clotting disorder that spread through European royal houses, descended from Queen Victoria, and became infamous enough to earn the nickname the royal disease. Hemophilia isn't caused by Rh factor. It's an unrelated genetic condition tied to the X chromosome. But the underlying story is the same one we just told about the Basque. Small, closed, intermarried populations tend to concentrate whatever rare genetic traits are already circulating inside them, for better and for worse. It's entirely plausible that some royal lines also carried elevated rates of Rh-negative blood simply as a byproduct of that same insular breeding pattern. Though hard genetic record from centuries past are far harder to come by than the folklore around them. Here's where the story turns from curious to genuinely tragic, and it's the part of Rh-negative history that isn't speculation. It's documented medicine. Before the late 1960s, Rh-negative mothers faced a quiet, poorly understood danger. If an Rh-negative woman carried a baby who inherited the Rh-positive protein from the father, and if any of the baby's blood crossed into the mother's bloodstream, which can happen during delivery, miscarriage, or certain complications, her immune system would treat that protein as a foreign invader and build antibodies against it. The first pregnancy usually went fine, because the exposure typically happened too late in that pregnancy for the antibodies to matter. But the second Rh-positive pregnancy was a different story. By then, the mother's immune system already had a standing army ready to attack, and it would cross the placenta and target the baby's red blood cells directly. The result was a condition called hemolytic disease of the newborn, a serious and often fatal complication for the child. For generations, families experienced this without understanding why. A woman could deliver one healthy child and then lose every pregnancy after it, with no explanation doctors of the time could offer. The breakthrough in understanding came in the late 1930s and early 1940s, when researchers including Karl Landsteiner, Alexander Wiener, and Philip Levine worked out the mechanism, that the mother's own immune system, sensitized by an earlier pregnancy, was the source of the danger, not any external illness. It took nearly 3 more decades of research after that before medicine had an actual fix. A treatment developed in the late 1960s, given to Rh-negative mothers during and after pregnancy, that prevents the mother's immune system from ever building those antibodies in the first place. It's now a routine, unremarkable part of prenatal care in most of the world, one of the quietest success stories in 20th century medicine, even if almost nobody thinks about it unless it directly applies to them. This is where things get genuinely puzzling from a pure evolutionary standpoint, and it's worth sitting with the math for a second. Natural selection is usually described as ruthlessly efficient, a trait that makes it harder to have surviving children should get weeded out over time, because the individuals carrying it simply leave fewer descendants. Before modern medicine, A genetic pattern that put later pregnancies at serious risk should have been under exactly that kind of pressure. Some geneticists have pointed out that, run through simple models, a trait working against reproductive success that directly should have been driven down toward rarity within a relatively small number of generations, yet it hasn't disappeared. It sits stubbornly around 15% of the global population and far higher in specific regions. There are a few competing explanations, and it's worth being upfront that this is still an active area of research rather than a settled question. One idea is that the Rh-negative variant may carry some kind of counterbalancing advantage that offsets the reproductive cost, something that helps the people who carry it survive other threats even as it creates risk during certain pregnancies. Researchers have explored whether the absence of the Rh protein affects how certain pathogens interact with red blood cells, since many infectious agents rely on specific surface proteins to latch onto and invade cells. Some preliminary studies have also looked at whether Rh-negative status correlates with different responses to the parasite Toxoplasma gondii, which is carried by cats and has been linked in various studies to subtle changes in reaction time and behavior in infected individuals. A handful of these studies have suggested Rh-negative individuals may show less of that particular effect. But this research is limited, the sample sizes are often small, and it's far from a proven protective mechanism. It's an interesting thread, not a confirmed superpower. Another possibility researchers have raised is simpler, that the Rh-negative allele has just been lucky. Genetic drift, random chance in which versions of a gene get passed on, especially in smaller or more isolated populations, can allow a neutral or even mildly disadvantageous trait to persist far longer than pure selection math would predict, particularly in populations like the bass that stayed small and isolated for long stretches of time. Neither explanation cancels the other out. It's entirely possible both drift and some yet unproven biological advantage are playing a role at once. Now, because this topic touches blood, royalty, and ancient mystery all at once, it hasn't stayed confined to genetics journals. It's become a magnet for internet folklore, and it's worth separating what's documented from what's pure speculation, because the two get blended together constantly online. You'll find claims that world leaders are secretly members of a hidden Rh-negative bloodline running the planet from behind the scenes. This doesn't hold up to basic fact-checking. Publicly reported blood types of recent U.S. presidents, for instance, show them carrying common Rh-positive types like the rest of the general population, not some rare shared marker. You'll also find communities online built around the idea that Rh-negative blood is evidence of extraterrestrial or starseed ancestry. The notion that people with this blood type feel a persistent sense of not belonging on Earth because their lineage supposedly